Poisson distribution. The next discrete probability distribution that we want to cover and talk about here is called Poisson distribution. Let's see what it is. We use the Poisson distribution when we are interested in the number of times that an event occurs, the number of successes, in a given area of opportunity. Let's see what is an area of opportunity. An area of opportunity is a continuous unit or interval of time, volume, or such area in which an event can occur more than once. For example, the number of scratches on a car's paint. So we define the number of scratches, quote, air quote, as success here, for example, if you are an inspector. The area of opportunity here is paint. It's a surface, right? Or another example, the number of computer crashes in a day. So the number of computer crashes is considered as success here, quote unquote, which is an event that we are interested in, not necessarily a good thing, of course. Day here is the area of opportunity. So the area of opportunity is a surface, if you want to consider it physically, that includes the success, the events of success here, right? So the number of computer crashes in a day, that's the area that it occurs. Another example, the number of telephone calls one might receive per day. So a success here is receiving a telephone call, and the area of opportunity here is day, right? So as you see here, the difference that we have here with the binomial distribution is the concept of area of opportunity that we have here. That's a main difference, and we're going to see more differences later on. Let's see how Poisson distribution is different from binomial distribution. In Poisson distribution, unlike binomial, there are no fixed number of trials. If you remember the binomial distribution, if x follows a binomial distribution with parameter n, the number of trials, and p, so n here is the number of trials. That means that the experiment has been repeated n times. For example, you toss a coin 10 times, and that's the number of success, if you define it as heads, would be anything between 0, 1, 2, 3, up to 10. You cannot have more than 10 heads because you tossed the coin 10 times, right? So n here is an important parameter in binomial distribution, but in Poisson distribution, we don't have the fixed number of trials. That's actually important because also the number of successes can be limited in binomial distribution by n, but since we don't have it in Poisson distribution, that means that in Poisson distribution, we can have almost infinite number of success. In binomial distribution, however, we are bound to n. You cannot have more than n success or failure. Another difference. The number of failures cannot be counted in Poisson distribution. Oftentimes, we realize it is meaningless to count the number of failures. So let's go back to an example from binomial distribution. Suppose that we toss a coin 10 times. 10 is our n, the fixed number of trials, and the probability of success is 50%. So if you define, for example, success as getting a heads, then if you get 6 heads out of 10, then you're going to have 10 minus 6, which is 4 tails, right? So if n is 10 and you get x equal to 6 tails or success, 6 heads or success, then n minus x, which here would be 10 minus 6, equal to 4. So you're going to have 4 failures here. So we can actually count easily the number of failures. The number of failures would be n minus the number of success. But this is not actually true in Poisson distribution. In Poisson distribution, we cannot really count the number of failures. Most of the time, it doesn't even make sense. For example, If we, going back to the example of Poisson distribution as the number of scratches on a surface of a paint or a car. So if you define a scratch as a occurrence of a scratch as a success, then you can count the number of scratches. That means that you can count the number of success, but you cannot count the number of failures because the number of the failure here is not having a scratch. Can you count the number of non-scratches? It doesn't even make sense. Or for example, if you define the random variable, the Poisson random variable here as the number of phone calls or messages or emails that you receive in a day, then it doesn't make sense to count the number of failures because the number of failure because failure he would be not receiving an email or not receiving a message or not receiving a phone call. How can you count the number of non-receiving messages, right? It doesn't even make sense. So in Poisson distribution, this is a big difference from a binomial distribution. Let's do a quiz, a simple question. Assuming potholes occur randomly along roads, the number of potholes per mile of road could best be described by binomial distribution, Poisson distribution, continuous distribution, cannot be determined from the given information. What do you think is the answer here? So please pause, think about this question, and let's see what is the answer. All right, let's see what is the answer. Can the number of potholes in 1 mile would be a binomial distribution? So first of all, having a pothole, occurring the pothole is a two output decision, is a two output possibility. Is either you're gonna have a pothole or not have a pothole. So that's a success and failure, two outputs. So that's actually checked for binomial distribution. However, do we have the fixed limited number of trials here? No, we don't. But it seems that we have the area of opportunity here, which is per mile. That's the area that the potholes, the number of successes can happen, right? So it looks like it's Poisson distribution. So it's not a binomial distribution because we don't have the number of trials here. Also, if you look at it, another difference that we saw here was that in Poisson distribution, we cannot define the number of failures. In binomial, we can. So can you count the number of non-potholes? It doesn't even make sense, right? So it can't be a binomial distribution. So let's see if C is true. Is it a continuous distribution? The number of potholes, you cannot have 6.8 number of potholes. You cannot have 10.2 potholes in a road, right? So it is not clearly it's not a continuous distribution. So C cannot be correct either. D cannot be determined from the given information. Well, it looks like that it's a Poisson distribution. So why not? It's a Poisson distribution. So the answer is B. Let's see the function for the formula for the Poisson distribution. So we already learned about the formula for finding the probability of x success, x number of success for binomial distribution. Let's see what is the probability, the formula for Poisson distribution. This guy right here is Poisson. He was a French mathematician, and in his honor, because of his work for this distribution has been named after him. This is the probability formula for a number of successes in a Poisson distribution. The probability of having x number of success is equal to e power negative lambda, lambda power x divided by x factorial. For x equal to 0, 1, 2, 3, up to infinity. Because x here is the number of success that you can have. Since we don't have any fixed limited number of trials here. This is a Poisson distribution. That means that you can have infinite number of success here. So that's why X can be infinity here. All right, so let's see what is these components of E and lambda here. So X is the number of events in area of opportunity, often as success here. The area of opportunity could be a time interval, a specific physical or geographical location, such as area or surface. And lambda is the expected number or the mean, the average of events. So it's a parameter related to Poisson distribution that we're going to learn about it more later on. E is the mathematical constant based on the natural logarithm, which is on average E is 2.71828, etc., etc. So E is the natural number, the Neperian number, also they call it the Neperian number. P of X is the probability of success, having X number of success in the given area of opportunity, given the expected number of success is lambda. Nothing can actually enforce us learning statistics and mathematics in general than doing a practice problem or an example. So let's see an example here. The number of customers who enter a bank within a given time interval is thought to follow a Poisson distribution. There you go. The problem already itself says that it's a Poisson distribution. If the mean number of customers who arrive per minute at a bank during 12 p.m. to 1 p.m. time interval is 3, then what is the probability that in a given minute exactly 2 customers arrive at a bank? This is the formula for Poisson distribution. So please pause, work on this problem, try to figure out what is this probability, and then come back to see the solution. All right, let's see the solution. So X here, the random variable is the number of customers who enter a bank within an area of opportunity. The area of opportunity in the interval of time between 12 p.m. and 1 p.m. So this is like 1 hour, which is 60 minutes. 60 minutes is our area of opportunity. And it clearly actually the problem tells us that this is a Poisson distribution. So the number of customers arriving, if you consider that as a success, each customer that arrived to the bank, if you consider that as a success, then you are looking for the number of success, the number of customers that would enter a bank in a given time interval, which is 60 minutes from 12 p.m. to 1 p.m. So this is an example of Poisson distribution. X, we define it as the number of customers who arrive at a bank, number of customers. I'm not going to write the rest of them because this is really difficult to write with the sliders. So X here, the number of success, which is the number of customers arriving at a bank, this actually follows a Poisson distribution. And we show this by lambda. Lambda is the average or the expected number of success here. So we need to figure out what is lambda here. And the problem is asking what is the probability that in a given minute exactly 2 customers arrive at a bank. Okay, and we need to now figure out number of lambda here. If the mean number of customers who arrive per minute at a bank is 3, so that means lambda is 3. Right, so lambda is 3 in a given minute from 12 to 1 p.m., which is 60 minutes. The expected number or the average number of customers that enter is 3. So we have lambda. Now we can plug in the numbers into this formula and find the probability. All right, lambda is 3, probability that we get exactly 2 customers. The question asks for exactly 2 customers, the probability of exactly 2 customers. So we plug in the numbers knowing that E is 0.27 whatever. You can use your calculator to do that, and lambda is 3. So we get the probability as 0.224. So the probability that we get in a given minute from 12 p.m. to 1 p.m. two customers exactly enter a bank is 22% or 0.224 to be exact. So we learned how to use Excel for binomial distribution. Let's see how we can use Excel for Poisson distribution. So to compute the probability of X number of success using Poisson distribution, you just write the probability of X equal to X, for example. If you want to have exactly X, a small x number of success in Poisson distribution, you write Poisson.dist, which is distribution, and the first parameter that you have put is X, the number of success that you're interested in, and the next one is mean. Mean is actually the lambda. And the last one is 0 here, which stands for exactly equal to. So this stands for exactly equal to. So if you were looking, for example, for less than that, that means that you were looking for cumulative one, then you would have to use 1 instead. So if you're looking for exactly equal to X, you have to use 0 here. If you're looking for less than or equal to X, then you have to use 1. And you can actually also find the probability using Excel. It's very easy. You just plug in the numbers and it's going to compute it for you. And you can also plot the probability distribution, which here it looks for X for lambda equal to 3. This is how it would look like. Before the inventions of computers and calculators, you can imagine how hard it was to compute or calculated the difficult formula computation. So they used to have a Poisson table that they use for computing probabilities back in the time. This is how it looked like. The first column actually shows the number of successes. This is just a part of the table. And then the column in the next column shows the first row is actually the lambda here. This is lambda. So we have for lambda equal to 0.1, 0.2, etc., etc. And using this actually, they can actually find a probability of the interest. So for example, let's see, suppose X follows a Poisson distribution with lambda equal to 0.5. And you wanted to find the probability that you would get exactly 2 number of success. How we would find that? So you could actually use this table to do that. You have to identify X equal to 2, that would be here. And then lambda equal to 0.5. So that would be the intersection of this would be the solution. So that would be 0.758. So the probability would be 0.758. This is how they used to find these probabilities because they didn't have calculator. So we can actually now use this equation, the formula, and plug in the values of lambda equal to 0.5 and x equal to 2, and using a calculator we can easily find this value, 0.755. Okay. Also we can use Excel, for example. Poisson distribution, the first parameter has to be the number of success, which is 2 here. The next one has to be lambda, which is 0.5, and the next one is 0 because we are looking for exactly 2. So we have to put 0. And if it was less than or equal to, it was cumulative, then the last parameter should be 1 instead of 0. Let's see the characteristics of Poisson distribution. The mean or the expected value of the number of success in Poisson distribution, mu, is equal to lambda. We already know that. The variance and the standard deviation of the number of success is sigma square, which is variance equal to lambda. So as you see here in Poisson distribution, the variance is equal to mu. And that's something new, unique about Poisson distribution. Its variance is equal to its average, its mean. This is a unique thing about Poisson distribution. And the standard deviation would be just a square root of sigma square, which is square root of lambda. Let's do a quick quiz. If the standard deviation for a Poisson distribution is known to be 3, the expected value of the Poisson distribution is A, 3, B, about 1.73, C, 9, and D cannot be determined. Which one do we think is the answer? And we have the formula down here. So please take a moment to think about this question and then come back to see the solution. All right, let's see the solution. So here we have the standard deviation equal to 3. That means that this is equal to 3. So a square root of lambda, which is equal to sigma, is equal to 3. And we are looking for the expected value. The expected value is lambda. So we have to find lambda here. If a square root of lambda is 3, this means that if we actually square each side of the equation, we get lambda equal to 9, right? So the expected value is 9, which is choice C.